Hello. So hi. Good afternoon. So let's resume our activities of this program. And it's a great pleasure for me to introduce the next speaker, Professor Luigi Ambrosio. And so he'll be giving a mini course on this thematic program, which is called Flow of Non-Smooth Vector Fields and Applications. So this is part one. Part two will be delivered by Alessio Figalli. Okay, so thank you.
So thank you very much. So first of all, let me thank the organizers for the invitation to be here. It's my first time in Brazil at IMPA. So let me start by explaining a little bit in informal terms what is the main theme of my lectures. So let's say that we are given a vector field B, which I will denote typically by B of Tx. So B will be also typically time dependent. Let's say in Rn, typically my time interval will be 0t. And then I would like to study the ODE associated to this vector field. So just to introduce a notation, I will denote by capital X the flow associated to B. So sometimes I will use the short notation Bt for B of Tx, right? And I will denote by 0x the initial condition. So the question is, under which regularity assumptions on B can we associate a natural flow map to this velocity field B? So let's say, let me write more precisely, can we define a flow map to B under low regularity assumptions? And by low, of course, I mean below Lipschitz, because under the Cauchy-Lipschitz theory, everything is known. Lipschitz, regularity on B. Of course, I mean regularity on B with respect to the space variables, because as in the classical Cauchy-Lipschitz theory, almost all results do not require any regularity in time, right? So let's say regularity on Bt to mean that I will be mostly concerned with regularity in the space variable. Okay, what should be the natural requirements of this theory? Well, the natural requirements of this theory should be, first of all, existence and uniqueness for almost every x, at least heuristically, but we will see that this is not the correct point of view. But we would like to say that in some sense, for almost every initial condition, we have a good solution, a good canonical solution. But what is even more important for the applications to PDEs is that this notion of flow map should be stable. So informally speaking, I mean that stability, by stability I mean that if, let's say, Bn, Bh converge to B, let's say that Bh are nice vector fields, satisfying some, let's say, LP bounds, maybe some conditions on the divergence and so on. And then if Xh are the classical flow maps of Bh, then we would like to know that precisely these classical flow maps converge precisely to the solution given by this theory. So then, let's say, if you look at the flow maps as functions of time, let me say more informally that this converges in the space of continuous maps, let's say for almost every x. Okay, so these are the two natural requirements of this theory. And as I said, particularly for applications to PDE, where many times solutions are built by successive approximations, this is really crucial. Okay, this theory started in '89 with a seminal paper by DiPerna and Lions. And then I revisited it, included other classes of vector fields in 2004. And since then, there have been many developments. And if you are interested in this subject, you can have a look. I will mostly follow these lecture notes. Which I wrote recently with Gianluca Crippa, that you can find at the CVGMT. Okay, and well, this covers almost all my lectures. Maybe it will not cover some more recent things that we did with Alessio and that he will illustrate in his lectures. Okay, so maybe to discuss these two issues, let me start from a very classical example, which is the square root example, the classical non-uniqueness example. So let's say that I study the ordinary differential equation gamma prime equal to gamma. And let's say I start from negative initial condition, which are the critical ones for this problem, with C positive. And then, of course, we know what happens in this case. We know everything. So we know that solutions reach the origin in time 2c. Then they can stay at the origin an arbitrary amount of time, which I will call t, maybe forever, or maybe they can leave at some time the origin, right? Okay, already this very simple example illustrates that maybe uniqueness for almost every x is not the right concept, right? Because here, for any negative initial condition, you don't have uniqueness, right? And so we will see already in this example what is the more natural point of view. Okay, let's discuss also stability in this setting. So for instance, you can try to approximate this by better vector fields. Let's say Lipschitz, but you could make them also C infinity. So let's say that I approximated this vector field B, 1D vector field, by B epsilon or gamma, which is given by this formula for minus epsilon square, then epsilon for minus epsilon square, lambda epsilon minus epsilon square. Lambda epsilon is a free parameter in this construction. And then gamma minus lambda epsilon plus 2 epsilon square for gamma larger than lambda epsilon minus epsilon square. Well, in this case, the behavior of the trajectories is similar, so they reach the origin well, they reach minus epsilon squared, not the origin, in a slightly smaller time, in time 2c minus epsilon. Then they move with constant speed for some time, and then they leave the origin. And then they move with this velocity. Okay, of course, this b epsilon is Lipschitz, so here we have no problem at the level of uniqueness. Clearly, b epsilon converges to this vector field. And if you play with this parameter lambda epsilon, you can select different families of solutions. In particular, if you ask that lambda epsilon over epsilon converges to a constant t, by this procedure, you select precisely the solutions which stay at the origin time t. Okay? So we have non-uniqueness here and sensitivity to the approximation. Okay, so how can we remedy to this situation? Already in this example, well, in some sense, the natural idea is to look for solutions. So the solutions with t equals 0 are the solutions which do not stay as little as possible on the singularity, which is in this case is the origin. Let's see how we can make this idea formal in a way which works also for more general situations. So to do this, let me open a parenthesis. And let me introduce some notation about push forward on measures. By maps. Well, this is a notation which I will use all the time in my lectures, and also I think they will appear also in Alessio's lectures. So let's say that I have two measurable spaces. And I have a measurable function f. And then, of course, there is a canonical way to push forward via f, let's say, probability measures or positive finite measures in x to positive or probability measures in y. And this is the so-called push-forward operator, which I will denote by f ds of mu, which acts in this way. Okay, so it pushes measures in x, goes in the same direction as f. It pushes measures in x to measures in y for any b in G. And more generally, I will not really use this definition, but I will use the change of variables formula for the push-forward measure. Which is an immediate consequence of the definition. So let's say that I want to integrate, for instance, a non-negative or a bounded test function phi with respect to the push forward. This is exactly equal to the integral of x of phi composition with f d mu. Okay, this is just apply this to the characteristic functions and then notice that this formula is linear with respect to phi. So it holds for characteristic functions, then for simple functions, and then by monotone approximation or by any other form of density for more general classes of functions. Okay, so now keeping in mind this notation, let's go back to our example. And let me assume that for any, let's say, for instance, for any negative initial condition, I select a solution. x naught. Let's say I will call x naught the solution, or maybe x. And you build in this way a flow map. So I don't have uniqueness, so this means that for any initial condition, I have a random time which depends on x, where I can stay at the origin. Okay, so let us assume that I impose, we assume that if I push forward with the flow map, the Lebesgue measure, okay, so now time is fixed and I consider this as a function of x, and with this function I can push forward the Lebesgue measure. Assume that, well, for instance, this is absolutely continuous with respect to Lebesgue measure, but actually much less is needed in this example for any t. Then by this way, we are selecting the solutions with t equals 0. So let me give you a proof of this. The proof in this case will be totally elementary, but I just want to convey the idea that also for much more general situations, this non-concentration condition will be the natural condition to select the trajectories. Okay, first I prove this, and then we make a comment about the meaning of this condition, why this should not be taught as a kind of almost everywhere uniqueness. Okay, proof. Well, since this measure is absolutely continuous, in particular it has no atom, so I know that for any t, which means that the Lebesgue measure of all x such that x of tx is equal to 0 is equal to 0, right? Just translating the definition of push forward. And this is true for any t, right? And so by applying Fubini theorem, I can invert these two quantifiers in some sense, and I can say that for almost every x, the Lebesgue measure of all times is equal to 0 is equal to 0. And so I'm precisely saying that for almost every x, I am considering the trajectories which stays at the origin 0 time, right? So this means that t of x is equal to 0 for almost every x. Okay. And of course, here in this example, we need much less. We need just to say that this is non-atomic, but we will see actually that for the general theory, the right condition is stronger than this one. We need the quantitative condition, not just absolute continuity, but a quantitative absolute continuity condition. Some comment about, let's say, almost everywhere uniqueness. Versus uniqueness in the selection sense. So we have already seen in this elementary example that this concept is the wrong one. And so the right point of view is this one, uniqueness in the selection sense. What does it mean? It means that in this example, I am able to select a family of solutions building a flow map. So this is a kind of global property of the trajectories. It's not an individual property of trajectories. I am able to make a selection in such a way that the flow map satisfies this condition. And it is precisely this family of selections, this kind of flow map, which is the good one, which we will see is also the one stable with respect to the approximation, for which we have uniqueness, existence, and so on. Okay? So this is actually the correct point of view, at least for the theory that I am illustrating, which covers Sobolev, BV vector fields, and many other classes of vector fields. Of course, there are more specific classes of examples where this phenomenon occurs. Okay. Now, before going really into the general theory, I want to provide some let's say, some motivating examples or some, let's say, relations and applications to PDE. So let's see. Let's start, for instance, from a very classical example. So I want to give examples where PDEs in mathematical physics, where vector fields, velocity fields with low regularity naturally appear. And maybe the most natural examples come from fluid mechanics. For instance, in dimension 2, for the incompressible Euler equation, if you write the equation in the vorticity formulation, so in terms of the curl of the velocity, you find an equation which has this structure, d over dt omega t plus the divergence of bt omega t is equal to 0. In SQL, I will call continuity equation any equation which has this structure. So the derivative of a function plus the divergence of this function multiplied by the vector field. So I will call it continuity equation. But in the incompressible Euler equation, there is a coupling between velocity and density, which says that up to the sign, if you rotate your velocity, the rotated velocity is the gradient. So you take omega t as the datum, the right-hand side of a Poisson equation. You solve the equation, you take the gradient, and the velocity is the rotation of this gradient. So in particular, the divergence of this vector field is equal to 0. So you see that in this case, we have a coupling, an instantaneous coupling between velocity and density. And of course, just from the classical elliptic theory, for instance, if you start from LP, let's say, to avoid the critical cases, between 1 and infinity, in general, this equation preserves the distribution of the vorticity, so omega t will not be better than LP. And so this means that by elliptic regularity, that Bt will be W1P. Okay? And now the question is, to what extent this equation still is related to the evolution, in some sense, from the Lagrangian point of view, right? So what happens if we study the ODE associated to this vector field with low regularity? This is a first example. Well, other examples arise simply changing the coupling, the instantaneous coupling between velocity and density. For instance, we retain the form of the continuity equation. I will call this a CE continuity equation. But let's say that still in dimension 2, we have still the continuity equation, but the coupling, for instance, a model which has been studied in recent times is that Bt is equal to the optimal transport map minus the identity, again with the rotation, which makes this divergence free. And the TT is the optimal map from some given reference measure, which I will call nu, which is time is not dependent on time, to omega t. And again, in this interpretation, omega t will be a measure, right? So I'm doing the optimal transport problem between some reference measure, for instance, Lebesgue measure on a domain, to omega t, and this changes the instantaneous coupling. This is called the semi-geostrophic equation. And here, depending on the regularity of nu, in general, you have only BV regularity, but under some assumption, this regularity can be improved to Sobolev regularity. But in any case, still you have a low regularity for this vector field. And another example in connection with the kinetic equation is the Vlasov-Poisson equation. And maybe Alessio will say something about this next week. This is also covered in a recent work I did with Maria Colombo and Figalli, but of course here there is an enormous literature behind. The structure of this equation, now we are considering a family of probability densities in phase space. And again, the structure of the equation is of a continuity equation in phase space. So the divergence will be in X and V, and I have this vector field times F equal to 0. And what is the form of the vector field in this case? Bt is equal to V. So the first n components are very regular, even linear, and the coupling between velocity and density appears here, and the ET is some constant epsilon times some positive dimensional constant times the convolution rho ft, where rho is the density in space induced by ft. So rho t of x is the integral of ft x v dv. Okay? So again, this is up to the sign. Epsilon can be positive or negative. This covers the electrostatic, the applications to, for instance, to plasma physics, or the application to gravitational physics. So up to the sign epsilon, again, we are solving an elliptic equation with the right-hand side given precisely by the density in space induced by ft. And of course, even in this case, the problem of low regularity of the velocity appears, unless you really look for very classical solutions with very strong assumptions on the initial data. Okay? Okay, and maybe just very quickly, let me say also another field where vector fields with low regularity appear. This will be very brief. And for instance, for some systems of conservation laws, for For instance, the most famous one is the Kaifitz-Kranzer system. Well, typically you might have this structure. You might have a transport equation. Okay, I will call in the future always this form of the equation transport equation. And you see the difference between continuity and transport is that here it is conservative and here it is not conservative. Of course, formally the two are equivalent if the divergence of the vector field is 0, but in general they are not equivalent. And typically the velocity bt is generated by a scalar conservation law. And so typically bt will only be v by the regularity theory or conservation laws that can develop also singularities in finite times. So in some sense, this is even worse than these examples because the regularity goes even below the Sobolev regularity in some applications. Okay. So these are somehow the motivating examples. Okay, now let me go back to the general theory. So in my lectures, I will basically forget about these more precise models where there is an instantaneous coupling between velocity and density. And I will focus on the ODE problem. So the common theme of my lectures will be how we can relate the ordinary differential equation to the partial differential equation. And by partial differential equation, I mean, well, depending on the context, but mostly I will cover the case of continuity equation or transport equation, where I mean the following, that the velocity is given. So I forget about the coupling. The velocity is given. And I would like to show you how there are general mechanisms which allow to transfer uniqueness and existence from the ODE level to the PDE level, and conversely from the PDE level to the ODE level. In particular, one of the ways to show that there is a well-defined, unique, and stable ODE is to study the corresponding problem at the PDE level. Okay? So I will devote a lot of time to this idea of how to transfer mechanisms between these two viewpoints for, let's say, existence and uniqueness. Okay. And before going really into the technical aspects, let me tell you what are the two basic connections. And we will see more sophisticated ones, but let's say the most basic ones. Well, the first one is that the ODE. Let's say weighted by an initial measure mu bar gives solutions to the continuity equation. Okay, so let's make this argument rigorous. So let's say we have an initial measure mu bar. Of course, give weak solutions because the continuity equation is in conservative form, so it should be understood in the sense of distributions. Okay, so let's see how we can make this rigorous. So assume that, again, I have built by this bunch of solutions a flow map, at least for, and I have an initial measure mu bar. Let's say that at least for mu almost every initial condition, I have built my, I have selected a trajectory, and then I call mu t the push forward by this map of mu bar. And now I will check that mu t solves the continuity equation. Of course, basically in all the applications that I will give in my lectures, mu t eventually will be absolutely continuous measures, so we can identify them with functions. But it is very important conceptually to think that the continuity equation has to do with evolution of measures of probability densities, while the transport equation has really to do with the evolution of functions, right? Even if maybe in the divergence-free case is the same equation, but it's important to keep them distinct. So let's see. Let's apply the definition. So I take a test function phi, it's infinity with compass support in Rn, and then this is equal to the integral of this is equal to the derivative. Okay, the first step is to apply the definition of mu t, right? And the change of variables formula. So this is the derivative of phi composition with the flow map d mu bar of x. Okay. Now, again, here there is an application of Fubini because I know that for almost every x, this function is differentiable in time for almost every time. So I can invert and then I can write, thanks to Fubini theorem, this as the integral of the derivative times b d mu bar of x. And then again I apply in the other direction the change of variables formula. This is precisely the integral nabla phi dot bt d mu t. Okay, which is the weak, precisely the one of the many equivalent weak formulations of the continuity equation. To be more precise, what you prove by this argument is that so here we have differentiated in time and we have chosen a test function in space. At the level of distributions, this means that what we proved is that d over dt of mu t plus the divergence of bt mu t is equal to 0. Let's say in the duality with all test functions C of t phi of x. But it is well known from the theory of distributions that with these test functions you can generate all smooth by approximation by all test functions. And so this class is sufficient to check the weak form of the continuity equation. And actually, we will see that my axiomatization of the theory of flow is based precisely on this mechanism. However, it is also important to mention the mechanism which was used in the original paper of DiPerna and Lions. And to illustrate it, I need to introduce a slightly richer flow map, which I will denote by y of tsx. So let's say that y of tsx is the solution at time t starting from x at time s. So in particular, to connect with this other notation, and then the principle which is used in the DiPerna and Lions paper to build all the theory is that the maps solve the transport equation. Okay, so let me give you a proof of this fact. So these are the other classical connection between, let's say, the ODE point of view and the PDE point of view. Well, we start to prove this. We start from the semi-group identity. So of course here I'm assuming that everything is smooth. Okay. So the semi-group identity, which is true in the presence of uniqueness, tells us that if at time L you start from x at time L and you reach the position y s l x, and then you restart, then by uniqueness you get the same result as y t l x. Then the right-hand side is independent of S, so I can differentiate with respect to S. And I get, by differentiating with respect to S, I get that d over ds plus, now I differentiate with respect to the x position. And here I have to differentiate y with respect to s, which gives me precisely bs x. This is equal to 0. And so you see that after a change of variables, if you call this maybe y, what we proved is precisely that all these maps solve the transport equation. Okay, so these are the connections between the points of view. Okay, so now the plan is to first I would like to remind some classical facts from the Cauchy-Lipschitz theory, because also this is important to provide some a priori estimates, which sometimes are useful when you work by approximation. So let's say Cauchy-Lipschitz theory. And a priori estimates. Okay, so let me assume now that we are really in the classical theory. So to be more precise, that B is in L1, W1 infinity. And of course, in this case, we know everything. So we know that there is a unique flow map. And also by differentiating, this is a simple computation, by differentiating square, we get that this is less than the Lipschitz constant of Bt times y squared. This is a simple computation, which uses, of course, the regularity of the vector field. And then via Gromval, you get also that the flow map, this is a very particular case which does not appear in all the other low regularity examples. In this case, we have that the flow map has the same regularity as the velocity. There is no loss in regularity. And so we get that the Lipschitz constant of the flow map is less than e to the integral between 0 and t of the Lipschitz constant of Bs ds. Okay, maybe I erase. And in this case, we know by the example I made before, which was independent of the Lipschitz assumption, that mu t, which is equal to mu bar, solve the continuity equation. And actually, I will not prove here uniqueness, but under this assumption, it is the unique solution to the continuity equation, right? I will speak about uniqueness in the next lectures. Now, I just want to give a priori estimates. And this is true for any measure, mu bar, initial measure mu bar. But of course, we can try to compute explicitly what is mu t. So let's try to compute mu t explicitly when the initial measure is absolutely continuous. Let's say mu bar is equal to rho times Lebesgue measure. And to do this, we need the area formula. Let me remind you the area formula for Lipschitz maps. Okay, what is the area formula is the change of variables formula, which is true for Lipschitz maps. The general formulation is that the integral so let's say you have a Lipschitz map f from Rn into Rn, Lipschitz. And then this is equal to the integral of the sum y dy. Sorry, let me check. G of x, of course, yeah. And here is f to the minus 1 of y. Okay, so I'm going to apply this formula where f is precisely my flow map at time t. And then f is also injective because, of course, the ODE is reversible. Also, the backward ODE has uniqueness, so this means that the flow map is injective in this Cauchy-Lipschitz theory. And so this is equal, in this situation, this is equal to the integral on, this is equal to the integral on f of a of g composition with f to the minus 1 dy. Okay, and also in this case, actually we will prove this more precisely later on. Also, the determinant of the gradient of f is non-negative, and actually it's always positive, so I can remove the modulus. Okay. Okay, now let us apply this formula with a particular form of G. So this is a general formula for F injective and with positive Jacobian determinant. Let us apply this formula taking as a G precisely rho over the determinant of the gradient of F. And you get that the integral on A or rho dx is precisely equal to the integral of rho over the determinant of the gradient of F composition with f to the minus 1 dy. Okay? Which tells me precisely that mu t as a density, remember that f now is this function. So this formula tells me, this is now really the definition of push forward, right? And so, so this tells me that the explicit formula for mu t is precisely the initial density divided by composition to the minus 1, okay, times Lebesgue measure. So, but as you have seen, for the verification that mu t solve the continuity equation, we don't really need the explicit formula. We need it only to perform some a priori estimates, as we will see in a moment, because it will be important for the development of the theory to know when my solution to the continuity equation has bounded density. Okay, so it will be important to know when, let's say, under which assumptions I know that the density of mu t with respect to the Lebesgue measure is bounded. And if you look at this formula, you see that what matters is that the determinant of the gradient of the flow map should be away from 0. And the precise bounds on well, less than exp. And here, the assumptions on the divergence of my vector field will start to come into play. Right? If I want to get a good a priori estimates, and here I have the positive part, and if I want to bound this from below, I have an analogous estimate, and here I have the negative part. Okay, and so for the development of the theory, it will be very important to control this away from 0. So this means that the bounds on the negative part of the divergence should be under control. Okay, and where maybe a few comments about where these upper and lower bounds come from. Well, star. So how the proof works? Well, if everything is very smooth, let's say BT, let's say at least C2, we can linearize the ODE. And we can linearize the ODE and prove, this is classical, that the gradient satisfies a linear ODE. Okay? So the matrix nabla X shows this linear ODE with constant coefficients, and then independent of X. And then out of this, if you take the formula satisfied by the determinant, you will find immediately that the derivative of the determinant and here you will find the trace and of course you know that at time 0 is equal to 1, and just by integrating this ODE you get immediately these two bounds. Okay, what happens in the non-smooth, in those non-smooth situations? In the non-smooth situations you argue by approximation. Actually, there is still a way to give a sense to the linearized ODE, but it is better maybe for this purpose to forget about trying to give a meaning to this linearized ODE and just try to get these bounds by approximation, right? So, for instance, you can mollify the vector field. And then, of course, since we are in the Cauchy-Lipschitz theory, the flows are stable, right? And so the flows x epsilon, of course, converge to x with equi-Lipschitz bounds. And then there is a non-trivial theorem by Reshetniak saying that if you have a family of maps which are uniformly convergent and which are equi-Lipschitz, then the determinants of the gradients are weakly star convergent in L-infinity to the determinant of the gradient of X. So even if this is a nonlinear quantity, it goes to the limit under weak convergence. This is a famous result by Rashetnia. And we can achieve the same bounds by approximation. Okay, maybe now I use the last minutes for a few more comments on the Cauchy-Lipschitz theory. There are two important variants of this theory. So we made this assumption that B was L1 with values in L-infinity, meaning that we were bounding uniformly the L-infinity norm of the vector field and the L-infinity norm of the gradient at the same time. So there are, however, two important variants of this theory, which are, of course, almost classical. For sure, the first one is very classical. Let's say that we make only L1, but only locally in space. Well, of course, without additional condition, then we know only that there is a maximal solution. You might have blow up infinite time and so on. But if we combine this with, let's say, the integral then the same results are true. Well, because we can use the growth condition to control locally uniformly the trajectories, and then, of course, we need only local Lipschitz regularity in space. This is more or less classical. Maybe the second variant is less known, but it is very useful. So in some sense, in some applications, we don't know what is the natural measure to grow. So in some sense, here we are saying that the natural measure to control the growth of the vector field is the Lebesgue measure. But in some other applications, it happens that you already know that there is a density transported by the flow. And I think we will see an example in the next lecture. Okay. And then it is natural to replace, so we retain this condition. Okay, maybe I will call this condition A, B. So we know that there is a density transported by the flow. Then we add, again, the local regularity condition. And then we modify B as follows. We impose a growth relative to the density transported by the velocity. Okay, under this assumption, what happens? Under these assumptions, one can prove, of course, one can't prove that the solutions do not blow up in finite time. It might happen because we have only a local Lipschitz condition. But one can show under this condition that still the Lagrangian representation is true. In this sense, then these three conditions imply that the maximal solution to the ODE, which always exists under, of course, under this only condition, we have always a maximal solution. Exists for mu0 almost every x. And of course, no other information can come from different initial measures. And still we can say that we have a uniqueness result that mu t, this solution which was transported by this flow, is precisely the push forward under the flow map. Let's say exists, let's say in 0t. So here, of course, I have this equation in some time interval. Exists in 0t for almost every x, and I have the representation formula for all t in 0t. Okay. Well, a technical comment I forgot to make is about the continuity equation. Many times, especially when I will be speaking about uniqueness, as you see also here, I state the result for all t, right, and not for almost every t. This requires an explanation because, in general, the distribution of solutions can be modified in a negligible set of times, still remaining distribution of solutions. So maybe for today I will stop with this technical remark. Which I will always use in the next lectures. So existence, let's say existence of a weakly continuous representative mu t. So what do I mean? I mean that you can start from a solution to this equation in the sense of distributions. Let's say with the mu t non-negative, otherwise the statement becomes more difficult. And as I said, in principle, you can modify mu t in a negligible set of times, and then it still remains a distribution of solutions. However, we can do the following. So if you take any test function phi, we know that we have this formula. So in particular, I know that this function is W11. It's in the Sobolev space W11. And so it has a continuous representative. For any test function phi, I have a continuous representative of this function. And then by a density argument, so playing with a dense set of test functions, and here there is also behind the dilemma that a positive distribution is a measure, of course. By a density argument, one can modify, let's say, mu t in a negligible set of times to get mu tilde t with, of course, now this formula becomes that mu tilde t is absolutely continuous. So it's really a continuous, not only absolutely continuous function for any phi. It's infinity with the compost support. Okay, and so in particular, this statement, for instance, is useful also to state in a simple way the initial condition. I take the continuous representative, and then the initial condition for my PDE becomes much more elementary to state. So I will always work in the future with this distinguished representative. And okay, I think for today I will stop here because what I have next is this chapter about the relations between ODE uniqueness and PDE uniqueness, which is better to start with fresh with a new lecture. Okay, I'll stop here.
Okay, so thank you, Luigi. It was very nice. Is there any question?